Wait, I muted. Okay, yeah, thank you very much, Vern, for your very kind words. So let's try to make a nice session out of it. So let's see if I can share my screen. Let's try to do this session a little bit more interactive. And without, okay, I think you are seeing okay. So yeah, so we have here the our space. We go to the our space, and you should see now this part. And then this is the latest version. Let's do a copy of this space. And please, again, if you have any question or anything important to say, just interrupt me. And today we are going to talk about relatedness, one of the important, I guess, arguably one of the most important applications for genetic data, which has a lot of insightful things. But one of the disadvantages of this method is that often is very difficult to get accurate estimates if we are not sure about how we the characteristics of our datasets. So for this session, we are going to use the RMD file. Let's go first to inst, then tutorials, and then the workshop number 16, and open the RMD file. Okay, so to make it look nicer, let's go to the visual part. And hide this one. Maybe I'm maximizing a little bit this. Maybe we can start by running the first chunk, which sets the different libraries, the different datasets we are going to use today, and the scripts. These are still in testing, but will be available very soon in the current version. Okay, here is more or less a session overview of today's session. We are going to do a very small introductions about what is relatedness. We are going then Ethan is going to introduce us to two different and very interesting datasets. And then if we have time, that I don't think we can do also some exercises. Okay, so as I was saying, relatedness is one of the important applications of genetic data, and there are also different versions of how we estimate or what is actually relatedness. For example, you might have heard about pedigrees, parentage, relatedness, kinship, and all those are different. They have different definitions or ways to understand the data. But I think the most important thing here, or the most important concept to understand relatedness, is the concept of identity by descent. So we can say that two locations, no, I'm sorry, one location in the genome, a locus, and the allele in that location is identity by descent in two individuals when that allele is the same allele in the ancestral population. So they are an exact copy that was inherited. And that's different from identity by state. So you might have the same allele, but sometime in the past, it happened that two different ancestries had the same mutation. So they are identical by state, but they are not identical by descent. Of course, it's going knowing about whether one allele is identical by descent and which allele is identical by state is very difficult. But as we are dealing with thousands of SNPs, the difference between identity by descent and identity by state is not that different. Okay, so and here is the other one. So we have relatedness, which is a measure of the proportion of the alleles that are identity by descent between two populations, between two individuals, in the context of a reference population. And that's also this. The reference population is also a key parameter in when we are estimating relatedness. So we, of course, we are just sampling some individuals, the current individuals in our data set. They are contemporary samples, but we are actually don't have information about the ancestral population. So in most of the relatedness methods, this reference population is actually taken from our current dataset. So that's one of the disadvantages of the relatedness values. As if we have some if our samples violate some of the assumptions of the relatedness methods, our estimates are going to be biased. And what are those assumptions of the relatedness methods, of most of the relatedness methods? So if those assumptions are that our data set is just one panmictic population, that the individuals are unrelated, and that there is no genetic structure. Okay, so and here is the other important term, which is kinship. So kinship is the probability that two alleles are identical by descent. So based on this, we have to make sure different methods estimate kinship or relatedness. So we have to make sure that, or we need to know whether we are estimating relatedness or kinship. So based on this, is the kinship coefficient is half of the coefficient of relatedness. Not always. For example, in inbred populations, kinship is not equal to 2 times relatedness. So two of the most important things that bias the estimates of relatedness is when we have a genetic structure. So when we have, for example, two different populations in our dataset and we are estimating relatedness, we are violating one of the assumptions of the relatedness methods. So in general, and in the mean relatedness, the mean pairwise relatedness between all the individuals in this dataset with two datasets, in no, in this data set of two populations is going to be lower than expected, because when we are comparing pairwise with individuals between the two populations, the mean average of the estimates is going to be lower, if that makes sense. And then the other way around, if we have one population, one data set in which all our individuals are from one family group or are very inbred, the mean relatedness between all the mean pairwise relatedness between all the individuals is going to be lower than expected. So a couple of things to do that that Ethan is going to talk to you in the examples is, for example, that if you have two very clear populations in your data set, the best way to analyze this type of data set is separating the two populations into, for example, two different gen-line objects, and estimate relatedness separately in each one of the populations. And in the other example, when you have an inbred population or a data set with inbred individuals and a lot of close relatives, one thing is that you can, to try to deal with this bias, you can also remove those individuals that are related. Okay. So, and one of the nice methods that has been published a couple of years ago is this method from Jillian Wang, which is called EMBD9. So, and this method actually uses a maximum likelihood framework, and very nicely takes into account all these bias in bred populations and in small populations. We can see that this function has a special parameter to estimate relatedness in bred populations, which you can find in GLRun EMBD9, and you can find the information in the help page. If you go here, and here, for example, this special parameter is here in breed. So if you set to true this parameter, it will use the inbreeding algorithm to correct for this bias. And also another nice feature of this program is that we can also use a parallel true and use as many cores as we have in on our computer. Actually, these the binaries for using the parallel version is not working, but we have been working together with Jillian Wang, and he has provided us with the source code of the program, and we have compiled it for different systems. And so if you have problems running the parallel version with other systems, you can write to us, or email us, and we can provide those binaries if you are having problems.
You can also use the beautiful GL download binary function to get the binary.
Yes, exactly. And also we have plenty more of functions to estimate relatedness and plot different relatedness in networks and in different heat maps that, of course, we don't have time today to go through each one of those functions, beautiful functions. But here, for example, we have the GLGRM function, which uses genomic relationship matrix with a nice heat map. Here in this specific example, we cannot see a lot of a very clear pattern in this plot, but it is all a matter of using a different palette. Yeah, that maybe we cannot. Yeah, if you go in the try to explore different color palettes here, and you will see that you will find very different patterns if you use a different color palette.
Can I very quickly, even if Luis is harsh to himself, maybe I put there. You can learn actually quite a lot from this. It's almost like, I'm not saying that usually is like a PCA, but when you look at it closely, you have the color from which population individuals are and how related, and you can clearly see three kind of blocks. These are the individuals within the population, and they have higher relatedness values than between the population. So you can see here also the population structure if you want it. And you can see also, if you look at the dendrogram, how closely, for example, if you look at the blue guys, you see some which are really have a short branch. The related values is fairly high. And then you have some are just really low. So you can, I'm not saying this is a good idea, but if you're looking as a first instance, for example, of individuals which are funky outliers, you could go for the one with the long branches in the blue sections and check if they are special. And they turn out also in the PCA differently, you get a good idea. So I think it's a highly underutilized method to estimate relatedness and then look at it and get some idea. I'm not saying this is the definite answer, but it makes sense to look a little bit longer at these plots.
Yeah, for example, look at the difference. Yeah, this is the correct one. Should be this one. Yeah, now you can see a better pattern here, how the different populations are more related within populations, and we have three different clusters. This cluster from one population, this cluster from the other population, and this one. And this, for example, these two populations, the red one and the green one, they are in the same river, but one is below the dam and the other one is above the dam. And this is a continuous river. And yes, and here we have the GL-run EMBD9, which runs very nicely and is very quick, even if you don't. Yeah, it's not working here. Yeah, for example, we need for the when you download the binary, you might need sometimes to grant access from the system to the binary. We do this using this command, and then we run again the program, the function. Sorry, and yeah, and then we got the nice result that we can use. There are a lot of different outputs in this. For this function, you can actually a nice feature of these functions is if you use the inbreed parameter equals to true, it will give you a square table in which the diagonal is the inbred coefficient for each one of the individuals. And also the other important one is that is also very nice to run is
gives you the related matrix. Maybe you can show that, Luis, if you want to. The relatedness matrix. Ah, there it is. Yeah. Okay. Basically, how related these different individuals are, and yeah. Okay.
Yeah. And then we have the year-round colony that is not actually the colony program is actually a very nice program also from Wang that do a big and broad several different analyses in one run. So if we run it, for example, it doesn't actually give you relateness values. It estimates or it infers the parentage and ship between the individuals, which is a different method than relateness. And also it's a bit tricky or sometimes very difficult to get it wrong because the input file is very, very messy and putting all together is very difficult. But just with this function is just really easy to run the function. Yeah, and just I'm going to run it again because I put the outputs in the temporal directory. But if we run it in the, let's see very quickly all the different outputs of this function and put it in the working directory. Okay, now we have all these, there are more than 30 different outputs. We even have an estimate of effective population size, which is also is different to the linkage equilibrium that Robin was talking about. And sometimes, most of the time that I have tried, that I have used both methods, both of the two methods agree very nicely. And for example, other interesting outputs from this function is the clones output, where we have, for example, these two individuals are the same individual, and these two also are the same individual, and we have plenty of different results that if you see the manual, you will get a very nice description of each one of these outputs. And I think I'm going to pass the presentation to Ethan. Thank you very much.
Thanks, Luis. Beautiful, beautiful description of the basics of relatedness there for us. All right. I'll just start sharing my screen in a second. All right, we're back. So basically, to wrap all these functions here up into a nice single function, we've produced this gl.diagnostics.relatedness function. So it's basically a wrapper that allows the user to call GRM, EMIBD9, and coancestry from a single function call. So we've basically just done this to make it a little bit easier, and so you can compare the results of those different methods all at once instead of having to sort of do all this convoluted folding and combining of data. It also includes the ability to run right Fisher simulations using the glsim wf.run function, but there's more documentation for that on the GitHub, so we won't go through that today. So this is just a basic run of what an input might look like. So here we've got our gl.basic.run calling gl.diagnostics.relatedness. We've got our input data here, platypus.gl. We have cleanup false, so we can go cleanup true, which just says whether we'd like to do a basic cleanup of the data, you know, fault, just removing all NAs, monomorphs, that sort of thing. We can also specify which tests from the coancestry package we'd like to run. So in this case, we're going to run Wang 2002 and Lynchard, but there are up to 7 different estimators you can run at once. We can also say whether we'd like to include plots, whether to include EMIBD9, in which case we will say yes in this case, where the actual EMIBD9 binaries are stored. In this case, they're just stored in our data folder. And then we can include whether we'd like to run it as parallel, and then this included ped is just whether you've included a pedigree in the data set. So that just allows for the output to actually benchmark all the outputs of those relatedness methods and just compare them to the pedigree. So we'll just do a basic run here. It shouldn't take too long. Just go here. There we go. So here's the output from our glbasic.run object. So we've got the input. This is a sim output. We haven't run the sim, so that wasn't the case. We haven't done correlation because there was no pedigree, so we couldn't compare the variance of our actual estimates to the pedigree. But the most important thing here is we've got our plot list. So if we go glbasic, we can access all our inputs here, and we go plot list. Just see again, here we've got our one plot here, which is just, these are our different estimates. So we've got Wang, Lynchard, this is a RR-BLUP, which is also used for the gl.grm function. So this is the base dartR estimator, and then we've got our EMIBD9. So as you can see, even on this sort of quite basic data set, there's already quite a bit of disparate analysis going on here. So each of these different estimators have sort of quite different estimates of what the actual relatedness value is. So that just sort of tells you that even with quite good and simple data, there can be quite a bit of variance in how these methods actually estimate relatedness. So this is just going through what I just said. So we'll move on to our first example. Peppa Pig gets an S&P panel. So our first data set is derived from some S&P panels that were generated on approximately 3,500 pigs, which were sampled from commercial farms across the United States. So the most important thing to note here is, in addition to these S&P panels, we've also got access to quite a large life history information. So we've got age, sex, and most importantly, parentage. So we have access to that pedigree that we can benchmark our estimates against. The other thing to note is that because this is an agricultural data set, we know this contains substantial genetic structure. So we're sort of expecting there to be at least one, if not two, subpopulations. And we expect there to be some degree of genetic structure. So it's violating basically most of the assumptions that are held, that are held by these estimate methods. The main one being that this is not a single pan-mictic population, and there isn't one large shared allele frequency distribution. So there should be more than one allele frequency distribution between the multiple subpopulations. But first things first, we'll just start with some basic data cleanup in QC. So I'm sure you guys have seen all this if you've been following from the start. We'll just filter on core rate, which, as you can see, the core rate was already quite high to begin with. We'll then filter some monomorphs, remove those monomorphs, filter for excess heterozygosity, and then we'll just remove minor alleles as well. So just with that basic QC done, we can just run a very basic PCOA plot, just with 2 dimensions. So in this case, we've used the gen to FBM function, so that just converts it into that FBM data structure like Bert and Luis were talking about the other day, and it just improves the speed of that PCOA. So as we can hear, so as expected here, we have these 2 really distinct populations that are sort of segregating themselves out along this first PCOA axis. So it's pretty obvious here that there's quite a strong degree of genetic structure present within this data. So just to sort of double check and make sure that that is in fact the case, we'll do a basic run of utils basics.stats. So what this basically done is just does a very basic calculation for inbreeding coefficient, expected heterozygosity, and then the main thing to note here is if you want to include subpopulations. So whilst we haven't done it yet, we'll show you how to do it down here. Just for this input, we've actually coded these 2 populations. So we've said this is population 2, this is population 1, just so we can actually have an estimate of the allele frequencies within each of the subpopulations. So we'll just run that now. So as you can see here, there's a slight excess of heterozygotes. So as you can see here, so this FIS, which is our inbreeding coefficient, is less than 0, which would suggest that there's in fact an excess of heterozygotes. In addition, the total expected heterozygosity, in this case, sorry, the expected heterozygosity across the whole population is less than that between each separate subpopulation. So this would suggest that we're not dealing with one large panmictic population, but rather these two subpopulations with one large panmictic population, but rather these two subpopulations with very distinct allele frequencies. So this basically just further cements those PCA values and suggests that it's really important that we should treat these as two separate populations when we actually go to do our relatedness estimate. So for purposes of illustration, we'll actually run our first relatedness on that whole population just to show basically what a bad output would look like. So we won't run this right now because it's quite a large population, but we'll just read in our data set, and then we'll do our first plot output and our second plot output. So the main thing to note here is we'll only focus on parent offspring, full sibs, and half sibs, because for a lot of estimators, the accuracy tends to decline quite rapidly past half sibs. So we tend to get sort of this really severe overestimation with first cousins, half first cousins, and second cousins. But as you can see, for parent offspring, full sibs, and half sibs, every single estimator has overestimated the actual relatedness value. So this is pretty expected, given that, as observed, that sort of total heterozygosity for the whole population is higher than for each of those subpopulations. So it's sort of overestimated that relatedness value. And we can also see this here. But the most important thing to note here is that there's quite a bit of disconcordance in each of our methods with regards to, so this here is, so this is the total number of counts of each pairwise relatedness here for these relationship levels. So we have our parent offspring are red, full sibs are orange, and half sibs are green here. So as you can see, EMIBD9, for instance, tends to vastly overestimate the number of second cousins when compared to, for instance, Lynchley or Lynch-RD. In addition, it also tends to overestimate the number of parent offspring versus basically every other estimator. Whereas GLGRM seems to vastly overestimate the number of second cousins. So this would basically suggest that as a result of this genetic structure, it's sort of throwing off all of these estimators, and we're getting this vast difference in their actual estimation of what the actual related levels are. So to sort of counteract this, as we suggested before, we'll just separate them out into these two separate groups. Now we'll do this quite simply. We'll just do it basically based on that first PCA axis value. So this will be our population A to the left of the PCA axis, and this will be our population B to the right of that second axis rather. So we'll just do that now quite simply. And then we'll show you the output of what happens when we run this again just on group A. So as expected, this has improved the fit of our parent offspring, full sibs, and half sibs. So they've all their estimates have generally come down for the most part to be more in line with what the actual expected values are, which are these dotted lines taken from that pedigree input. As you can see, for certain ones, for parent offspring, EMIBD9 is still somewhat overestimating it. But that's to be expected, given that EMIBD9 actually expects a smaller population with higher levels of parent offspring. So it sort of makes sense it would overestimate it to begin with. But for the most part, for most of our estimators, this has already improved our fit. That's also the case here. As you can see, say for EMIBD9 with that estimate of parent offspring, all of these estimators look basically the exact same, which would seem they all sort of agree on what the actual relatedness levels are. We'll do that again for group B. So as you can see, that's also the same. All these estimates have all improved and they've come down more, so they're sort of more in line with what the actual values are. Also the case here, once again, EMIBD9 is slightly overestimating it, but once again, that can be expected given it assumes a base level of relatedness that's slightly higher than the other estimators. So with that being said, we can move on to our second example. So this example involves data drawn from the Soay sheep. It's a primitive breed of sheep descended from a feral species found on the island of Soay in the St. Kilda archipelago. Just like the pig data set, we have quite a large life history. So we have whole SMP, microsatellite, and whole genome data in addition to an extensive manually coded pedigree and a rich life history of sex, parentage, and age. So we've chosen this data set to provide an example of a data set that would be the inverse of the previous pig data. So in this case, we expect this data to more or less conform to the assumptions of our pedigree methods. So it's a large population that's panmictic. That is, it's randomly mating freely, and there's relatively little inbreeding when compared to our previous results. So just as before, we'll just do a quick sweep of that data set and filter on call rate, monomorphs, add minor alleles. So just to see what, if any, structure exists, we'll just do a quick PCA again, just in 2 dimensions. Take a second. So as we can see here, there's a little bit of a tail out here, but for the most part, these results are basically congruent with a single population. There doesn't seem to be too much separation out of 2 subpopulations. But once again, just as with the pig data set, we'll do a quick run of the utils.basic stats. And as you can see, our inbreeding coefficient here is a little bit lower than what was observed for the pig data set. Obviously, because we have no subpopulations here, there is no subpopulation heterozygosity frequency, so it's just one frequency here, calculate for this whole population. But just based purely on this FIS value, it's safe to assume this is a slightly less inbred data set with slightly less structure than was observed. So we should expect our analysis right away to be improved over that seen in the pig data set. So we'll have a quick look at our plots here. So as expected, these estimates are basically bang on. Obviously, with this one, there seems to be quite a bit of variance, but it's just that the y-axis range has sort of been thrown off. So in reality, if we look here, the range is almost identical to that observed here, so between 0.2 and 0.3. Would suggest that once again, it's a little bit of an underestimate, but for the most part, the estimates are, without any real editing being done to the data, they're already improved over what was observed for that initial pig data set. Same with down here, same except for EMIBD9, which once again is sort of slightly overestimated. That parent offspring level, all these values are more or less the same, and all the methods seem to broadly agree. So with that being said, we can now walk you guys through some basic a basic exercise, just sort of going through this on your own with some data that we've provided you. So the setup is you spent the last 6 months studying the platypus and been trying to understand the genetic basis for its famous bill. To understand the molecular basis of this trait and how it is inherited, you've collected samples from 81 individuals and constructed a pedigree by hand from known crosses observed in the wild. You've lost that pedigree, unfortunately, and now have to rebuild it from scratch. You have faith in the dartR package, however, and decide to use it to try and reconstruct your lost pedigree. So the first things first, you guys can start with some data read in the data, some filtering, just be sort of fill in the data as you go here. Some data QC, just that PCOA plot. You can do a quick check on report heterozygosity or the utils.basic.stats as before, and then just do a quick relatedness run with the GL diagnostics.relatedness. Just to be sure here, guys, when you're doing true false, replace this with a character and go true or false. So yeah, so if you guys would like to work through these exercises over the next sort of 10 to 20 minutes, we'd be more than happy to sort of walk you through it. But other than that, if you guys had any questions, we're happy to field some questions now just before then.
Hey guys, there are a number of questions. You want to answer them now, or you want to yeah, I guess we go there, isn't it? There are quite a few.
Yeah. Lewis, would you like to help answer some questions?
Yes, happy to. Yes, of course. Do you want to finish first, or should we go to the questions as you wish?
No, I think maybe we can do the questions, and then these guys can work through those exercises in their own time.
Okay.
Start with the first.
Okay, I go through them. Or are you doing that, Luis? Okay.
No.
I mean, I present you the questions. The answer, yeah, okay, I try, but you can do as well.
If we want to calculate relatedness or kinship and we have structure, is it better to separate groups and then make the analysis, or can we make analysis considering that all individuals come from the same population or groups? Sure, Liz will agree with me, but as said before, it's probably best for you to separate them out. There's a few ways to do it, but the easiest way is just to sort of code them like that and make sure that the subpopulations are sort of separated out. Because like I said, if you run them all as one large group, when that's in fact not the case, then all those methods will assume the allele frequencies are the same across the whole population, which is clearly not the case as we provided there. So that can throw off all those estimates. So by all means, you can probably run them, your initial analysis as one group, but it's probably best to sort of separate them out as you go and then do them sort of separately. Luis, do you have anything to add?
Okay. I can jump in if you want to.
Yes, go.
It depends a little bit on the situation, I think. Obviously, if you have, all this related measure have one thing in common. If you need to estimate, in some sense, allele frequencies, and they should be unbiased. So in the best of all worlds, you would have a sample from the whole of the population and estimated allele frequencies. Yeah. And when I say population, then I'm totally agree with Ethan. If you have two of them, yeah, then you do that for one population, and for the other population, if you know they are totally separated, completely make fine. So you have an estimate of the average allele frequency for each of the loci, and then relatedness basically the excess of certain combinations of alleles, which is more than you would get by chance. That's basically your signal for being related. Problem with our data always is we do both at the same time. We sample a population, estimate allele frequencies, and then we try to infer relatedness. If your estimates are biased of the allele frequency, then also your estimates of the relatedness will be biased. And there's no, by logic, there's no way around that. What these methods try to do, for example, EMIDB9 tries to do estimate allele frequency and the relatedness in kind of a alternating fashion, tries to estimate allele frequencies, tries to estimate relatedness, and then kind of shrinks on the result. And therefore, EMIDB9 is meant to be better in some instances by dealing with inbreeding, because it takes this allele frequency estimates and the relatedness into account. It doesn't work, obviously, perfectly, as we can see, but it depends a lot on the structure of the population you have. If there's a lot of inbreeding, I don't think any of the estimates will help you to get a real unbiased estimate. It's almost, by logic, not possible. If you have a fairly good unbiased estimate of the allele frequencies, then probably most of the estimates give you similar results, at least, And it's, yeah, that's probably where I stop. So if you have two groups which are totally separated and they have their own allele frequencies, separate them. Yeah, if there's actually, it's more like a mixed population, then no, I wouldn't separate them.
I guess the other important project in which we have been working is actually trying to solve this problem. And seems that has been working very well. For example, the related package and ancestry. Yes, they have different approaches to simulate data, and then using that simulations to get an expected value and compare it with the observed value. Well, these approaches are not very accurate for many details, and we are trying to find a way to actually getting an expected value and then compare it with the observed value, which is maybe a bit more difficult to explain in a few seconds, but stay tuned that we are going to release something very nice very soon. Yes, so here is another important thing, because pedigree is also a different, is similar in theory that relatedness, but the problem with pedigree is that the pedigree is actually not taking into account whether the individuals are inbred or not. So in one of the papers from Wang's paper, he did a lot of different analysis. He estimated different estimate when they had a data set with the full pedigree and compare it with relatedness values. And the conclusion was that actually the relatedness values provide much more important information than just pedigrees. And yeah, and it's a subset. If you have a lot of inbred or related individuals in your data set, it's better to remove those individuals that have close relationships, because you might sometimes have other applications of relatedness. For example, you don't want actually to identify close full siblings or half siblings. You are more interested in identifying more further relationships, maybe because you are trying to identify closer enough relationships in a landscape that you can use this relationship for landscape genetics, or how different dispersal patterns occurs in the landscape using relatedness values and not precisely half siblings and full siblings. No, that was the opposite. We cannot use SilicoDart for calculating relatedness. Yes. Go, Bernd.
With caution, as you can see, because depends actually what you want to do. If you want to have parentage, obviously you want to have identify zips, and obviously the further you down go in the relative kind of hierarchy, it will be really messy. So the main thing obviously is maybe parent offspring and siblings and so on. And there you stop, and there you have a good chance. The method gives you, in some sense, also a confidence interval where the relatedness values have to be. And when you're outside or close to it, then you still can call it probably, say, a sibling, but you probably should be cautious. And if you don't have parentage information, the method will assign it in some sense to an offspring or to a sibling or whatever. But there is an uncertainty, and you get a little bit from the interval of the estimate, the uncertainty. Yeah, that's probably all there is to say, because you can't get it 100%. Yeah.
And here is another important application for simulations, that we can use simulations to
make. Yeah, and obviously, I should have answered that. Chris told me, obviously, simulations. That's what you can do. You try to simulate offsprings and give me your data set, and then you get the range of values, what you can get as a certain category of relativeness. Is that a word? And then you can see, yep, okay, my data set is good enough to have sharp boundaries, or it is actually all overlapping in terms of relatedness categories. You're muted.
Yes, I haven't thought about it, but definitely if the microbes and those kind of organisms, they don't follow the assumptions of the relatedness. So I think they would not be very useful for microbes.
About, because in sense you have, obviously if you have total different model of reproduction and inheritance, yeah, I'm with you. If they have some clonal things, and then it will be harder. Yeah, but if they follow sexual reproduction, I think you should have a chance.
Yeah, I haven't heard about that specific analysis. Sorry.
Yeah, I think fine rod structure is based on haplotype, so it is more a similarity coefficient compared to a relatedness matrix. So you get in the output, you get the same thing. You get an individual kind of how closely are two individuals together, but the basis is different. That okay. Oops. Oh. Yeah. That's really hard to answer. You would need many more details, and then again, my lame answer is simulations and have some pilot data and try and see how good the methods are. It's actually quite. I should have done that in simulation, but with the GLSim offspring function, you can use a genline object and simulate offspring, and then put it in your function and run GLEMIDB9, and then check how good they are to identify the offsprings, because you know them, simulate it, use your data, and then you have that. Anyone wants to chip in?
Depends on lots of things, but especially how far they disperse.
Sorry?
Depends on lots of stuff, but depends how far they disperse.
Ah, yeah.
You talk about area, then you decide.
Oh, the area, yeah, I ignored that. Sorry, yeah, Chris was just saying me that the question was also about the area, and that's really then dispersal becomes into play. How far do they move? Are we still good, Luis, to go?
Yes.
Okay. They're quite still a few. We're getting towards it. Okay, another question. If we are interested in the relatedness of a subset of a population, can we use the rest of the individuals as a background estimate of allele frequency in a population with high structure?
Yes.
Yes, that would be
yeah.
the ideal situation. Yeah, sorry.
Yeah, you go, please.
No, that's exactly what you would like to have, and there's actually methods where you do that. Basically, you estimate the allele frequency from an independent sample and use that to estimate relatedness from your individuals you're interested. That's exactly what you would love to have, but we quite often don't have. And most of the methods do it in one go, but that's not ideal.
Maybe we can finish a little bit earlier today, and I think there is the opportunity to respond to the questions later in the event. After the talks finishes, we can still reply to the messages. So we will reply to the messages, to the questions after the session. And if you come back to the session, we will be responding to those questions. Maybe we can finish today's